Hey everyone, and welcome back. In this lecture, we're going to have a look at matrix plots in Seaborn. We'll have a look at the two different types of matrix plot, which are the heat map and cluster map, as well as how to create them. Let's go ahead and get started. I've gone ahead and imported the libraries that we'll be using for this lecture, which are matplotlib and Seaborn, as well as import the two datasets which we'll be using, which are the MPG dataset that we've used before, as well as the car crashes dataset, which I've just assigned to two variables called MPG and crash dataset respectively. We've already seen our MPG dataset, but for our crash dataset, this is what the head of it looks like. It's just data on car crashes from different states in the United States, with information on the total number of accidents per billion miles in our first column, and then the percentage of accidents where alcohol was involved, and so on for the rest of these columns, and then with the state abbreviation at the end. The first type of matrix plot that we'll look at is the heat map. And this will probably be the main type of matrix plot that you'll use, and are actually very helpful. A heat map lets us easily see the correlation between different variables in our dataset. But before we can create a heat map, we'll need to convert our data over into the correct format, and this format is called a correlation matrix. With a correlation matrix, we have variable labels for our column headings and for our rows too, instead of the numeric labels that we've got currently. To turn our data frame, as it is currently, into a correlation matrix, we can call the .corr or correlation method on it. This method only works for numeric columns though, and as we've got an object data type column here at the end for our state abbreviation, we'll need to get rid of this. So we could either drop this column, but I'll just select all of the other columns using square bracket notation, which I'll fast forward while I do this. Okay, and then with our columns selected, we can call the .cor or corr method on this, and that will return a data frame, but with all of our columns in a matrix form, with the variable label for both our columns and rows, and then the numbers for each of our cells can range from -1 to 1, which actually shows the correlation of our data. With our data in this form, it's then very easy to create a heat map. I'll assign this correlation matrix to a new variable, which I'll call crash dataset correlation, and then I'll pass this variable into the sns.heatmap function like this. This plot then just visually shows the correlations in our correlation matrix by colouring the values in, but based on a gradient which we can see from our legend off to the right here. A stronger correlation results in this bright, almost whitish colour here, and then a weak correlation results in this really deep purple black colour. From this, we can easily see that there is quite a strong correlation between the number of deaths and if the people were either speeding or under the influence of alcohol, and comparing this to our original correlation data frame, we can see that these cells did have quite a high correlation, with a value of 0.61 and 0.85 respectively, which are again out of a maximum possible value of 1. And just to quickly explain here, a value of 1 shows a perfect positive correlation, and a value of -1 shows a perfect negative correlation, and 0 is no correlation at all. A positive correlation occurs when the value of one variable increases as the value of another goes up, or vice versa, whereas a negative correlation is just the opposite of this. So as one value decreases, the other value increases. The heat map just makes it a lot easier to visualize and interpret the results of our correlation matrix by drawing attention to any particularly strong or negative correlations. If we wanted to see the actual values for these correlations but on our heat map and not just a color gradient, we could pass in the ANNOT or ANNOT argument, which is just short for annotation, and then set this to be equal to true. And this will then display the actual values for our correlations so that we don't have to rely just purely on the color. For larger heat maps, Seaborn may not plot all of the annotations for each cell in an attempt to avoid cluttering your plot. Another thing that I'll quickly introduce are color maps, which we can use to customize the colors and color palette of our plots. We'll have a whole lecture on these later on in the section, so I won't go into too much detail now, but we could just say that CMap is equal to blues. And here we have to have a capital B. And blues is just one of the many color maps available in Seaborn. But as mentioned, we'll of course have a look at some more examples of these in our styling and color lecture. For now though, if we run this, we'll see that our plot gets a blue color palette with white for our low correlation values, and then a dark blue for our highly correlated values. Before we move on to our next type of plot, we'll have a look at one more example of heat maps, which we'll do on our MPG dataset. Let's quickly bring up the data types of this data frame by calling D types on it, and then have a look at which columns we'll select. So there are a few object data types here. I don't want all of these columns, so I'll just pick out the MPG, cylinders, horsepower, weight and model year columns, and then like last time, I'll call the .corr method on this to create a correlation matrix of our data. Instead of assigning this to a variable, I'll just pass this directly into our heatmap function. And then I'll also enable the annotation argument for our values, as well as setting the color map or CMap to blues. And then we can easily pick out which of these columns or grids have a higher correlation by looking at the darker grids. For example, the weight and horsepower columns are quite highly correlated, as is the horsepower and number of cylinders too, which is the result that we'd expect from this. We can also edit the line color and line width of our heat maps too. Currently, all of our cells are bordering and touching each other, but if you wanted to add some separation, we could first add in a line by specifying the line width and then setting the color of the line. I'll set a line width of 1 just to create quite a thin line, and then I'll set the color of this to be white. And now there's a small line running between each grid. So it's your personal preference if you like this or not, but it's just a helpful change that you can make should you want to. Okay, let's now move on and have a look at the final type of matrix plot in Seaborn, which is the cluster map. And basically, a cluster map just combines a heat map with something called hierarchical clustering, which helps to reveal the patterns and relationships in a correlation matrix, which it does by rearranging the rows based on their similarity to each other, as well as again colouring the values with a gradient, like our heat map did. And let's go ahead and look at an example to make this a bit clearer. I'm going to start by creating a new data frame which will contain all of the float and integer data types in our MPG data frame. Instead of going through and manually selecting all of these with square bracket notation, I'm going to introduce a new method we can use to do this for us. I'll start off by creating our variable, which will be equal to our MPG data frame, but then instead of opening square brackets, I'll put in a dot so that we can access our methods, and then I'll call the select_dtypes method. And this will allow us to select all of the columns with a particular data type inside of that data frame. We wanted the numeric columns, so I'll pass in a list containing float 64 and int 64. If we check the contents of this variable, then we'll see that it's just a regular data frame, but only with the data types that we specified before. And I'll then just go ahead and create a correlation matrix on this by saying numeric_mpg.corr, which I'll then assign to a new variable, which I'll call numeric mpg correlation. And with our correlation matrix created, let's go ahead and create our cluster map. The function to do this is just sns.clustermap, and then I'll pass in the data that we'll use, which will be the numeric mpg correlation matrix that we just created. And here is our cluster map. It's pretty large, so I'll just zoom out so that all of it fits on screen. And there we go. The first thing that we'll probably notice is that in the middle we have a heat map, just like before, which shows the correlations between our variables. And then we also have our gradient legend over here off to the top left, which shows us that lower correlations have a dark color, and then the more highly correlated values have a lighter color. To help us see this, I'll just pass in the annotation argument and then set this to be equal to true, so that we're able to see the actual correlation values. But as well as our heat map in the middle, you'll also see that we have some lines off to the left and top of our heat map. And these are the hierarchical clusters that I mentioned to you earlier. The technical name for these lines or hierarchical clusters is actually a dendrogram. And simply put, a dendrogram is just a diagram that shows the hierarchical relationship between objects. If we have a look at our X and Y axes, we'll see that our horsepower and weight columns have been placed next to each other. And this is actually not in the order that our columns will have been passed in. If we compare this to the heat map that we made before, then these columns got plotted in the order that we passed them in. But with our cluster map, they're in a completely different order. The reason for this is because with our cluster map, the columns that are most similar to each other have been clustered together. So basically, it's just gone ahead and clustered all of our columns or variables that are similar to each other and put them together. So for instance, we can see that our horsepower and weight column here are quite similar to each other, as are the cylinders and displacement columns. And then you get to see the level or hierarchy of our clusters with these lines, or the dendrogram, that we have off to the left and top of our plot. For example, the dendrogram shows a link between the MPG and acceleration column with a secondary cluster going off to the model year. And these clusters are further related to the horsepower, weight, cylinders, and displacement columns. So overall, this dataset is quite clustered, which makes sense as each of these columns is likely to have quite a large impact on each other column. And again, just to show you, this Cmap argument that we looked at before will also work with our cluster maps too. I'll just set this to Viridis, which is just another colour map that we have available in Seaborn. And of course, we'll have another look at the colour maps in our lecture on colours and styling. Okay, so that's it there for our lecture on matrix plots. Cluster maps are more helpful for machine learning and data science, but you should definitely make sure that you understand heat maps, as these are a great way to visualize any correlations in your data. So let's wrap this lecture up now, and then in the next one, we'll take a look at our final plot type, which will be grid plots. Thanks everyone, and I'll see you there.